Is there an ODP for today?
There's not.
Hallelujah.
I gotta figure out what, if any, ODPs I'm gonna do this week. So questions on trees or PA3? PA3 I'll go over tomorrow in class, but PA3 looked good. So questions on anything up to here? Yeah.
For the mode, are you allowed to have like a global variable or?
For the mode between stack and queue?
Yeah.
Yeah, you can make it global. It probably doesn't have to be, but that's okay if you do that.
Do that is by adding that into the node structure.
I think your main is the only thing that needs to know what mode you're in, because your main program, if the person says P, you're going to either want to pop from the stack or remove from the queue, depending on the mode. But if mode is defined inside main, it can call either pop or remove. Because you've got two separate structures, one for the stack, one for the queue, right? Two linked lists. And you just use whichever one the mode says to use. But if it makes sense to have it be global, that's fine. Got no problem with that.
What's with the backdrop? Are those birds?
Those are birds, yeah. Birds and trees. So I just found out my mom's been listening to my lectures. So say hi, Mom. Hi, Mom. All right, let me touch base on SLP presentations, which are coming up in a few weeks. So I posted this on Canvas. Just to give you a heads up on SLPs for this quarter. So as you go through your careers, you'll be writing papers and doing research and developing code or systems or things like that, and you may find yourself in a situation where you're wanting to present what you've been doing to other people in the community. And so usually there's two modes of these presentations. One, you write a paper and you send it in to a conference and they accept it, and then you go up to the front of a room at a certain place and time and you do a presentation to the people in the audience and talk about your work. The other option is what's called a poster session. And poster sessions let you have more people presenting more ideas at the same time. And so a typical setup will be at a conference, there might be 3 days of presentations, but maybe on the first night there's a poster session. And somewhere, typically the ballroom of a hotel, they'll open up the space and everybody gets a number. So you're number 17, and you find an area of the room with that number on it, and there's a place where you can put your poster on the wall. And so you've prepared either a single poster or a bunch of posters or a big thing that you got printed or something, and you put it up for people to see, and then there's usually food and drinks, and people come around and they eat some food and drink some wine and walk from station to station and talk to people. And it's like, oh, you're working on such and such, I'm interested in that too, what are you doing? And you get into a conversation. And that's kind of what we're trying to mimic a bit with the SLP presentations. Okay, so this is an opportunity for you to share your project, your experiences so far, your progress, right, and your ideas about where you're going next with this with other people. So the bulk of the other people are us, right? We're both the consumers and the producers of this shared information. Although sometimes we do get people from outside coming in to look at people's posters and stuff, especially in the June presentation at the end of spring. So the goal for this session is you're going to pick a spot in the digital lounge or in the hallway outside, right, somewhere. Find a table, either one that's out there, or you'll come in here and grab a table with a friend and put it down somewhere. And assuming you submit your poster on time, it'll be printed out for you. So you're going to take your poster, you're going to tape it onto your table. Okay, the poster is not going to move. If you have things to share with people, if you've written code and you've got something running on your laptop, if you've got a circuit you built or something you printed or whatever show and tell you may have, you can have that at your table also. Okay, some people in the past have brought in little candy bowls or little toys from the dollar store to get people to come over and look at their poster, right? And this is also very typical in poster sessions, trade shows, swag, right? Free stuff, you can go and pick up a little noisemaker, and now you talk to somebody about their poster, right? So the primary mode is going to be, you're going to be at your table with your poster and your show and tell, and people will come over to you and say, you know, hey, what are you working on? Or they'll read your poster and they'll ask you some questions about it. And you often find at the end of these sessions, you've got some new ideas or a new direction, or maybe some new questions to think about related to your project, right? So this is actually an important piece of the development process of the SLP. Because a lot of times we're working on these things alone, right, or in a group of 2 or 3 people, but it's a little closed group, and you might be stuck in one direction. You're moving down a certain path, and you're kind of not sure where to go next. And a 2-minute conversation with somebody else might be a light bulb moment. Might be like, oh, we don't even have to do that. We've got enough to go in this other direction, right? And it can like help refocus your whole effort. So this is a really valuable experience, and our goal is to give everybody an opportunity for this. So so your poster is going to stay on your table. Yeah.
First, it's March 12th?
Yes, as opposed to Mac 12th.
Yes.
Yeah.
And second, and if we need a TV screen or something to show off what we have so far, is that provided, or do we need to?
You got to provide it, yeah. So if you have a laptop, right, that takes care of it. If not, if you can find a monitor somewhere.
That's okay, because I can provide that.
Okay, cool. Yeah, I wouldn't plan on using the monitors in there. Occasionally people have, but it's not guaranteed that they're available. So.
And on that note, should we also provide our own power cords or extension cords?
Probably not a bad idea. There's plugs all over the place. There's plugs in the floor and I think on the wall, so usually you're pretty close to one. And if it's a problem, let me know, because we might have a stash somewhere. All right, so signature sheets. Signature sheets are not the purpose of the presentation. Okay, they're a little bonus to give people incentive to go and visit other tables. But your sheet only gets signed when you visit somebody. You look at their poster, you ask them questions, they give you their pitch about what they're doing, and so on. At the end of that exchange, you can say, can you sign my signature sheet, to say that I was here, and they can sign your sheet. They don't hand you their sheet at that point and say, tell me what you're doing, and you sign their sheet. Okay, you only get your sheet signed when you go and visit somebody's table and look at their poster and talk to them. Okay, so I don't want people walking around carrying their posters in one hand and their sheet in the other, and you know, right? Because that's not the goal, right? That gets you the signatures, it gets you your few points of extra credit, but the goal is people coming over and talking to you and getting some practice at presenting what you're doing. Because really, until you try to explain what you're doing to somebody else, you don't necessarily have as clear an understanding yourself as you will afterwards. So that's really valuable. So, so if you're working with other people, you can take turns, right? You stay here for 10 minutes, I'm going to go walk around and visit other people, and then you come back and your partner can go around for 10 minutes and visit other people, and so on. If you're by yourself, you got to kind of split your time. So some of the time you'll be standing there with your poster waiting for people to come over and talk to you. If nobody's walking around, right, put a sign up, you know, I'll be back at 2:30, and take your sheet of paper and go around and start visiting people. And it usually works itself out, right? So some people will be at their posters, some people will be walking around. So it takes some flexibility. Does that all make sense? So I put all the wordy details up there, but that's the gist of it, right? So so think about this as an opportunity to present your ideas and get some feedback from people that you're presenting to. All right, questions on trees? How many people are coding trees? Cool. All right, well, let's change gears. Let's talk about tries. So a try is kind of like a tree, but it's better. A try is a structure that we can use to store information and then go back and search for that information later. And typically we would be doing something like a hash. We'd be storing a name and associating some piece of information with it. Like, you know, office number and phone number and stuff like that. But to simplify our work here, we're just going to look at storing information in a try, just storing, say, names or words. And we're going to simplify our space to be just words containing the uppercase letters A through Z. So no spaces, no punctuation. We're just going to store straight words like this. And technically a try is a tree, okay, but it's not a binary tree. Your nodes generally have more than 2 children. In fact, they're going to have 27 children on each node. And we're not going to have kind of an inherent search order the way we do with binary search trees. So here's what a node is going to look like. It's going to have 27 entries corresponding to the letters A through Z. And then there's going to be one more entry down here, which I'm going to call EOS for end of string. And that's going to be a 1 or a 0. So this is end of string. Which is a 1 or a 0. Everything else here is going to be a pointer to a node, or it's going to be null. So similar to what we've done with other trees. Each of those 26 entries is either null or it's pointing to another node. And the last entry in this node is just a flag. It's a 1 or a 0 that we call end of string. Now the goal here is to have a very time efficient structure for storing and retrieving information. And this is going to be order 1. Absolutely order 1. No collisions, no most of the time or anything like that. It's always going to take a fixed amount of time to retrieve or store information in this structure. So if you have something extremely time efficient, there's got to be a penalty somewhere. What's the possible penalty for extreme time efficiency? Memory, space, right? This is our classic trade-off.
There's a spider.
Where's the spider?
Right above your.
Here, straight up.
Oh. All right. Spiders are good luck.
I'm sure they are somewhere.
Yeah. Could be in here.
Oh, yeah. Now I see it.
Is it like dangling? Oh, I see it. All right. Does anybody need me to take it out? Oh, not dangling anymore. It was learning about tries, man. It's like, dang, I'm gonna have to go to tomorrow's class and watch the video. So this is an eternal trade-off. So let me do a sidebar here. Time and space. We did a sidebar in the previous section on reversible computing, so you can watch the video if you want that. We're going to do a different one here, which is time and space trade-offs, also not on the exam. but something to think about as we're doing all of this stuff. We have different kinds of algorithms we can use, right? We can store information and try to retrieve it. And probably the most space-efficient way to store information is just put it in an array, just store it consecutively. Right? If you want to store a word, just take the next, a 5-letter word, just take the next 5 locations in memory and store your word, and then store a null terminator. And now you want to store the word cat, store a CAT in a null terminator. And now you want to store dog, store DOG in a null terminator. And just pack all your information, write one word after another with null terminators in between. That's probably, unless you compress, the most efficient way, space-wise, to store information. Right? Because in memory, we've got hello, cat, dog, spider. Right? So it's packed in there as tight as possible. But if you want to look for something, is there a dog in here? You really got to start with the first word, down to the null terminator, it's not a dog. Continue down to the next null terminator, right? Really, really inefficient. So that would be some point out here. Takes very little space, takes a lot of time. Okay, we can do a little better with an array if we just have an array of pointers to memory. But stuff gets spread out in memory. It's going to take a little more space. But if we alphabetize, right, we can do a fairly efficient search. So that's going to sit somewhere over here. If we do a binary tree, that's going to be very efficient because it's log n to do searches and inserts and deletes. But it's going to take at least twice as much memory because every node has 2 pointers associated with it. So that's going to be somewhere up here. And a try is probably somewhere over here where it takes a fixed amount of time but a huge amount of space. And it's not a straight line, but it's got a direction to it where basically if we want to take less time, we need more space and vice versa. And this happens architecturally when you design a computer. You can make a 4-bit computer, and we can add 64-bit numbers with a 4-bit computer. Right, so go back to the 70s, get an Intel 4004. You can do 64-bit arithmetic on that, but you do it 4 bits at a time. Right? You can do this on a PIC processor, it's 8 bits. And in 270 we talk about doing 32-bit arithmetic, or even floating point arithmetic, but you have to do it a little piece at a time. Right? But those hardware pieces, the PIC processor, the Intel, they're really, really small hardware. Right? So that's another curve where we have to do a lot of iteration, but we don't need a lot of space. Now we can get an Intel processor that's 64 bits, and it'll add very, very quickly, but the amount of hardware involved in that is much bigger. It's a physically larger device. And so there's another curve like that. And this is ubiquitous, right? We're constantly playing off space and time. This is not a place you want to be, because that takes a really long time and a lot of space. And this is really where you do want to be. Something that's really fast and doesn't take a lot of hardware or a lot of memory. And that's a really hard point to get to. But the closer you can get to that, the better off. So this branches off into my research interests because I like exploring stuff over here. Very, very space hungry, but very time efficient. Because we can't buy time, right? No matter how much money you have, if a calculation is going to take 1,000 years, you can't minimize the impact of that 1,000 years until you have a way to like hibernate for 1,000 years and then wake up when your computer's done running. We can't commoditize time, right? We can deal with space. I need a processor the size of Texas. If I've got enough money, I can buy the state, kick everybody out, and build my processor, right? That's doable. This is not. If it takes 1,000,000 years to get my answer, it takes 1,000,000 years. Right? So there's some different nature between space and time. All right, so back to tries. So how do we store something in this structure? Let's store a cat. Okay, so we're going to store the word CAT. Here's how we do this. So here's the root of our whole try, and it points to one node. So I'm not going to show every one of these 27 pieces in here. I'm going to use some dots, but there's a piece of this that points to A, B, C, D, Y, Z, and then there's the end of string marker. So I'm just struct try node. Might look something like this. So a struct try node might have 26 pointers to struct try nodes that I'm going to call A, B, C, D up through Z, and then it has an integer, which is my end of string. And in reality, I would put these in an array of pointers to struct try nodes, but it's easier to think of them as just 26 pointers. All right, so here's the root. This is a struct try node. And I want to store the word cat. Everything is null unless I say otherwise, and the end of strings are 0 unless I say otherwise. So all of these are null to begin with. Well, since we're storing a cat, we take the first letter C. We change this C pointer to point to a new try node. The second letter of cat is an A, so we're going to take the A pointer in the second node, and we're going to point to a third try node. And here, so these end of strings are 0. And here the third letter of cat is T, so we're going to take the T in this third try node, and we're going to point to a fourth try node. And here we're going to set end of string equal to 1. So what I've done is I've stored a cat into this try. And how do I know there's a cat here? Because on my root node there's a pointer from C, and the node that points to has a pointer from A, and the node that points to has a pointer from T, and the node that points to has this end of string flag set to 1. So that tells me I have a CAT end of string stored in my structure. Okay, so let's store a cab. So start off at the root. C already points to something, so I don't have to make a new node, so I'll come down here. Now the second node, A already points to something, so I'll come down to that. B doesn't point to anything yet, so B is my third letter. I'm going to have B point to a new node. And there I'm going to set my end of string to a 1. So now I've got a cab stored. Alright, let's store cats. So I'll start off with a C, that points to here. I'll follow the A, that points here. I'll follow the T, that points here. I'll take the S, I'll point to a new node. And I'll set my end of string to 1. So I've got C, A, T, S, end of string. So that means cats is in there. right, let's store dab. So I'll come out to D. D is null right now, so I'll have that point to a new node. I'll have A point to a new node. I'll have B point to a new node. And I'll set end of string to 1. Yeah.
Do you not want it to point to the first A? The C that's pointing to A. Do you want the D to point to A as well?
If I have the D point to the A, then I'm saying that DAT is part of my structure, which it's not. So we have to kind of make these new nodes, even though they're just being used to hold one letter, basically. Right? If the second letter is different, if any of the letters are different, right, from that point on, we're going to be on kind of a new path of nodes, basically. So really space inefficient, right? But that's okay. Okay, so how do we look for something? So is cab in our structure? Well, go out to the C, that points somewhere. Go to that node, see if A points somewhere. It does. Go to that node, see if B points somewhere. It does. See if end of string is set on that node. If it is, cab is in our structure. Yeah?
What if you're saying like cub for the C?
To insert or to search for? To insert. Okay, so let's put in cub. So start off with the C, that points down here. Come over here to the U. Point to a new one. And then set the end of string. So is car found? Well, start at the root. There's a C, it points somewhere. There's an A, it points somewhere. Check the R. The R is pointing to null. Car is not in our structure. I guess R will be over here. Okay, how about cabs? Start at the C, come down here, follow the A, come down here, follow the B, come down here, follow the S. S is null, cabs is not in there. Right, but cab, follow the C, there's the A, there's the B, end of string, cab is in there. Yeah. Any time that you have another letter and you're not currently pointing to a node. So let's see. So let's add CAD. So first letter is C, check the root node, see if C is pointing somewhere. If it's not, I'd have to make a new node and point to it. But C is already pointing to a node. So I'm just going to follow that, and I'm going to go to my second letter. See if A is pointing to something. It is, so I'm just going to follow that and go to my third letter. Now I'm going to check D, and D is null. Okay, so I need D to point to another node now. So I'm going to create a new node. And I'm going to go to my next letter, and there is no letter. I'm at the end of my string, so now I'm going to set the end of string to be a 1. So this is kind of quirky. One of the quirky things about this is our data is never actually stored anywhere. If I implement this in memory and I search all of memory, I'm never going to see a C followed by an A followed by a T. And that's unique with lists, with arrays, with hashes, with trees. If I store the word cat somewhere, I'm going to see a string CAT somewhere in memory. It doesn't exist here. The information is somehow an artifact of the way that these things are pointing to each other. It's sort of in the process of following these links that we can extract the words that are stored. So that's a little different. This end of string flag, right, I'm just using this as an integer, a 1 or a 0, to say that that's the end of a word. But we could also store at that point whatever we want to associate with this. So if we were doing something like a hash where we were trying to store words and then something associated with that, we could store that associated information in this piece of the node if we wanted. And this obviously only works if we have things composed of uppercase letters A through Z, but we could generalize that. Right? We could have more nodes. In fact, we could have 128 entries in here corresponding to the 128 ASCII characters, and now we could store anything comprised of ASCII characters. Or we could make it bigger and go Unicode. Or we could store binary information. We could break your...
Do all caps.
Or we could do all caps. Or we could break your binary file. Sorry?
You could change it to all caps.
You could change it to all caps if you didn't care about uppercase, lowercase. If you have a binary file and you want to be able to store binary information like this, we could break your binary file into nibbles, 4-bit chunks, and treat each of those as basically a letter, right? Something from 0 through 15. We could have 16 entries on each of these, and now we could store binary files in this structure by just following link to link to link to link. And then if you have a file and you want to know is that stored in here, we could go through the structure and look for it. So it doesn't just have to be words. It could be binary, it could be images, it could be frames from a movie, it could be complete movies, it could be sound from a WAV file or an MP3. Right, so it's a general structure. Huge amount of memory. But the time is really, really efficient. Because if your word has 10 letters, at most you've got to do 10, maybe 11 operations to either find it or store it in your structure. So if we're doing words, I don't know what the longest word is, but certainly words are bounded by, say, 50 letters. Most words have quite a bit less than 50 characters. 50 operations max to either store a word in here or find a word or confirm that it's not in your dictionary. And that's pretty efficient, right? Even if you imagine 50-letter word being the max, right? How many 50-letter words are there? It's like 50 to the 26th, right? Which is up there with the number of particles in the universe, I think. So huge amount of information, and you can plow through that and pull something out in 50 operations. That's pretty sweet. Right, that's better than log n. It's really order 1. Deletion does not work very well in this. Right, you can delete an individual word by just clearing that end of string flag. But if you want to actually reclaim space that you don't need anymore, that's harder. For example, if I got rid of all of these, right, I should be able to get rid of all these nodes. But knowing when you can get rid of a node and when you have to keep it around can be tricky, because I might get rid of cat, but I still need cats to be stored. So C, A, T. Right, I can change this to a 0. That deletes the word cat, but cats is still present. But if nothing here was pointing anywhere, right, I could get rid of this node and change a thing that was pointing to it to null. But it gets trickier.
Do you know how many iterations of a single word there are?
Basically, yeah.
That's a lot.
Yeah. But traversing this is not bad. It's actually pretty fun because it's hyper-recursive. So how would you traverse this and find all the words that are stored? I mean, we could do it by hand. We could start here and get down to a C. And so we'd write a C in our output.
It's like 2 lines of code.
Could be, yeah. There's a bit of logistics to keeping track of everything, but basically, when I find that C is pointing to something other than null, I know I'm going to get a bunch of words. If I traverse my try starting at this node right here, every word that I find, if I just put a C in the beginning, that's a word in my try. So I keep track of some kind of prefix, and I say traverse this tree, rooted right here, with a prefix of C. And every time it finds a word before it prints out a C in front. And what am I going to do to traverse this? Well, I'm going to find an A is pointing somewhere, so I'm going to say traverse this try, but print a C and an A in front of whatever words you find. And I'm going to come over here to U, and I'm going to say, okay, traverse this tree, but print out a C followed by a U in front of any word you find. And it's really just a bunch of calls to itself. You just have to keep track of what the prefix is up to that point, and you do some loop over all of your 26 pointers, and anytime you find your end of string is 1, you just print out whatever the prefix is that you were told to print in the front of things, and you know you've got that word. And again, these words aren't stored anywhere. They're coded in this collection of links, and we retrieve them by following these links and keeping track of what those links tell us. So it's a kind of fundamentally different approach to storing information. And it seems a little more like process-based somehow, which starts to smack of memories. All right, questions about this so far? Tomorrow we'll play around on the board for a little bit, and I'll have you work with this structure and put some things in and find some things, just to get some practice with it. I want to have people code these sometimes because they're actually really fun to code. It takes very little work, and you get this huge payoff for it. But I don't think I'm going to do that. Maybe I will.
Any other downside besides deletion using
Just the space. Just the fact that they take so much memory. And you can get around that. Instead of having a node with 26 pointers, you could make a linked list of pointers up here. And that gives you a bit of a performance hit. But you move along until you get to the letter you want, or you insert in the right spot and go on. And you're still bounded by roughly order 1. So tries were discovered, explored by someone named Fredkin. So we got 10 minutes. I'll go off the rails here and tell you about something that you don't have to know for the exam or for this course, but you should know for life, because it'll be a topic down the road when you're in the middle of your careers probably. This is the notion of reversible computing. And this was one of the things Fredkin studied when he was at IBM back in the 60s, possibly 70s, I'm not positive. Reversible computing, so so two statements, x equals x plus y, and then y equals x. So let's suppose x equals 5, y equals 10. So I said x equal to the sum of x and y, which is 15, and then I said y equal to x. So now x and y are both 15. And there's nothing wrong with that. But after I've executed this second instruction, suppose someone asks the question, what was x before you did this? X was 5, y was 10. I know their sum is 15. But after I'm done with this y equals x statement, do I have any way of finding out what the value of x was before I did this?
X minus, oh, yeah, X minus Y.
Yeah.
That'd be 0.
right? So it's possible that x was 10 and y was 5, or x was 1,000,000 and y was 1,000,000 minus 15, or 15 minus 1,000,000, right? They could have had almost any values. All I know is that their sum is equal to 15.
Couldn't you do like an interway of just saying like, every time when you do like this increment thing, you could just say, okay, the previous one is equal to this, and then increment the next array bit. So if you have like variable A0 would be the first x.
Okay.
Then you go through the computation, then variable A1 would be the next x.
Right. Okay. So we could do that. There are ways that we can try to preserve this information as we do calculations. And that would be a good way to do it. Although whatever was in that array A0 before is now lost. Or A1. But before we do that, is there a reason to worry about this? Is there some problem with destroying information? I mean, if we don't care about it anymore, if all we care about is the sum, why not just say x equals x plus y, y equals x? And what Fredkin discovered is that there is a downside to destroying information, and the downside is heat. And he discovered that when you destroy information, you actually generate a little bit of heat. It's a really tiny amount of heat. We don't even notice it today. And it's nothing compared to the heat generated by having electrons going through a wire facing resistance. Current times voltage equals power, right? That's the dominant term. That's where all of our heat comes from. That's why we have fans in our laptops. But a little piece of that heat is coming from the destruction of information. So here's what Fredkin was thinking. As our technology improves, as we use superconductors inside our computers so that there's no resistance, and we get perfectly efficient transistors that can switch but don't generate heat as a byproduct because they don't have resistance, and we get all of the physics down to the point where there's no heat being generated by our electronics, there's still going to be this little tiny bit of heat generated by the loss of information. And that might be a trillionth of a watt, right? But if you have a trillion transistors, each generating a trillionth of a watt of heat, that's a watt, right? And if you have 1,000 of those, that's a kilowatt, and that's a lot of heat, right? Now you've got a iron for clothing. And you can't get away from this. Right? So this is a fundamental limit. It's not a limit based on how good our transistor technology is or how precisely we make our wires and so on. This is a fundamental information theoretic limit. That if you destroy information, you generate heat. And the concern is that as computers get smaller, physics gets more efficient, and we get more and more components in our systems, this is going to be the dominant component of heat. And at some point, you're going to have to deal with it. And the only way, arguably, to deal with it is to stop destroying information. So the goal is to be able to do calculations but not lose any information in the process. So something like what Julian was suggesting, store these results along the way before you modify them. And if you store all of these, it's possible to run your calculations in reverse. Right? If we have this and we want to go back one step, we can only do that if somehow we know what the value of y was before we made this assignment. And we can only undo this if we know the value of x before we made this assignment. And we can't just get it from looking at x now. We got to have other information. So there's a thing called a Fredkin gate. And it's a logic gate with multiple outputs. And it not only does a logical AND of the two inputs, but it also gives you some extra information that you can use to go back and figure out what those inputs were. And so there's a lot of research in this, and there's Fredkin gates, and there's Toffoli gates. Google will correct the spelling for you. And there are different ways to be able to try to do calculations, to do information processing, but without losing anything in the process. And as a side effect, being able to run these calculations backwards. This gets into thermodynamics, fundamental laws of thermo, reversibility of certain processes, increasing entropy, all that kind of stuff. So if you've done thermo in physics, this is tied in. If you haven't, you can think about this when you get there. And it's a thing. It's not a major thing right now, but a lot of people think that down the road it's going to be a very dominant thing. And it's something that's going to have to be dealt with. And to me, one of the weird parts is, if you're not destroying information, are you actually doing anything useful? If all we're doing is transforming information into another form, but we're not actually getting rid of anything, is this transformed version of the information somehow fundamentally different from what we started with? I mean, if it's got all the pieces and you can get one from the other, they seem kind of equivalent. Why run a program for 3 months to get something out that's exactly one-to-one somehow with what you started with? So there's weird aspects in there. So if you get bored, do some Googling. Look up Fredkin gates and Tofeli gates. And see where that takes you. Not going to be on the test, but it's something that I think you should encounter somewhere, and you may not encounter it anywhere other than what we just did here. So there's your reversible theory for the quarter/year. All right, so tomorrow we will play around with tries on the board, get some hands-on practice with storing things in there. We'll go through PA3. I'll just make a few comments, show you some code for that. And then we're going to start talking about sorting and searching. And we'll spend about a week looking at different algorithms, mostly for sorting, beyond a bubble sort. All right, so I'll see you tomorrow.